Alright, it's time to bring this chapter home. So in this last section, what we're going to talk about is something that's very important in the human body, and that's buffers and buffer systems. A buffer is a solution whose pH will change very, very slightly when an acid or a base is added. Another way to word that is it fights, or it doesn't allow pHs to change like they would. So it resists a pH change. Alright, and most of these buffers are going to be a weak acid with its conjugate base salt. Okay, so a weak acid with its conjugate base. So remember, one of the weak acids we said was acetic acid. And so you would mix acetic acid and the sodium salt of acetic acid. Alright, so that's an acetate buffer. Alright, buffer resists changes because the added base reacts with the weak acid and the added hydronium reacts with the conjugate base. So if you're giving off protons because you added acid, because that's what you're doing, you're adding the protons, then you've got something there with an OH or other that's going to attach to that and make water. And so if you don't have free hydrogens, free protons floating around, the pH won't drop. If you add base, same thing, you're going to have something there that will attach to that and neutralize it so that it can't have a free hydroxide. So if you have a buffer solution, like for example, if you have like just water and the pH is 7 and you add acid to it, it's going to go down in pH quite dramatically. If you add base to it, it's going to go up in pH quite dramatically. But if you have a buffer added to your water and you add the, you say you're buffering it at 4.74, like you usually buffer them to stay around a certain pH. If you add acid to it, it might only go down to 4.70. If you add base to it, it might only go up to 4.77. So a very small change in pH. Alright, much smaller than if it was just water and it didn't have a buffer solution in it. So what does it take to make a good buffer? If you add an acid and so when you add the acid, if it's just in water, you're going to have excess acid and excess hydrogen ions. That excess acid reacts with your conjugate base so that the overall pH doesn't change. So if an acid is added to a buffer, the acid that's left over reacts with the conjugate base, and so the pH doesn't change. Because remember, what makes pH is free protons, free hydrogen ions. So if you have something that can then take these and reform the acid rather than the hydronium ion, then that's going to keep the pH from changing so much. In a base, you add excess base, then the conjugate acid is going to react and do the same thing, keep it from reacting, because your hydroxide is going to be taken up, and so you won't have free hydroxide, and so you cannot decrease your pH as low. So buffers are super important, especially in the human body, and we have several buffer systems. I mentioned earlier that normal blood pH is between 7.35 and 7.45. If we didn't have buffers, it would be impossible to maintain that small a range of pH. And so one of the big buffer systems, prominent buffer systems in blood, is the carbonic acid bicarbonate system. Carbonic acid is H2CO3, and the bicarbonate ion is HCO3. Notice the difference between those two. Okay, you lost a proton from the carbonic acid, so this is its conjugate base because it's missing one of the hydrogens. So what happens is, in metabolic processes, okay, you've got carbon dioxide, which has been given off by cells, which adds to water in the body, and it forms carbonic acid. The carbonic acid can then form with water and form hydronium ions and the bicarbonate ion. So you have bicarbonate, which can reform carbonic acid, and you have carbonic acid, which can form bicarbonate, and you can even go back further to CO2 and reform CO2 or form more carbonic acid. And so if the pH starts to go up, you can grab those hydrogen ions and go back to carbonic acid. If your pH starts to go down, then you can accept those from your carbonate. If you need to get rid of some, then you can also do that. So either way, you can decrease or increase the pH or resist the change, resist the increase or decrease. So that's why how much carbon dioxide you have in your blood is going to affect the pH of the blood, because if you increase this, then that's going to make more carbonic acid. And then when you make more carbonic acid, you're going to make more what? Protons. Acid. And so your pH can go low. So that's why you compensate in different ways. So if you're compensating with your respiratory system, if you have respiratory acidosis, you have not eliminated enough carbon dioxide, and this is usually due to a problem with your lungs. So if you have a problem with your lungs, you can't fix that problem with your lungs, right? So you're going to have to compensate with your heart rate or something else to try to get that to occur. And the reason that you have increased CO2 due to lung disease or failure is because you're not getting rid of this CO2 because your respiratory rate is too low. And since you're accumulating the CO2, that is driving this to the right, and you're going to increase the acid concentration, and that's going to lower the pH in your blood over time, and so you are going to be in what's called respiratory acidosis. Opposite happens with respiratory alkalosis, and you can see this if someone's been hyperventilating. They don't have enough CO2 in the body, and so their CO2 goes down. Because of that faster respiratory rate, you're getting rid of too much CO2, which decrease. And so if you're decreasing the CO2, that's going to pull this way, which means you're going to have less of your H3O plus, which is going to give you a higher pH because it's going to be on the base side, and that is going to cause what's called respiratory alkalosis. Much more rare than acidosis, but can be even more life-threatening.